Hello everyone, I hope you're keeping well and that you're all safe, whatever state you're in, isolating or not. I actually don't know who is isolating and who isn't, so I can't access the register, but I might ask that later on. Now, we're going to start. I know I set you a task on Seneca Learning to kind of go over sort of, the idea was really to get a sort of overview of the type of study we'll do in molecular covalent bonding, or molecular covalent bonding and molecular covalent substances. This is probably the largest. This covers, you can see, 4 different topics, right? And I've tried to put them all together and hopefully give you a story of covalent bonding and covalent structures that makes sense. So I have mixed up the points in the specification with the goal of trying to kind of build this story rather than just follow the specification, and hopefully it'll, and with plenty of practice, hopefully there won't be a question you cannot answer, right? Okay, so that's the goal. Now, just to give you an overview, a sort of story of how we're going to progress, right, of bonding, we're going to start with GCSE covalent bonding and sort of just modify it slightly. Okay, so the first thing is, and you don't need to take this down, right, actually I need to change my pen. Okay, so the first thing we're going to look at is covalent bonding, right? Now we're going to start with drawing diagrams, right? So you could call them, the old sort of GCSE ones were dot and cross diagrams, right? And we're going to move to what are commonly known as Lewis structures. Now, whether you use the old dot and cross diagram with the shells shown, or you use the Lewis structure, I really don't care as long as they're correct. I'm going to use the Lewis structures mostly because that's kind of what you'd have to do at university. So I think you should develop that skill, and you can always go back to the other type, the easier type, like the GCSE version, if you choose to. It's not going to make any difference to how you score in the exam. Okay, so drawing diagrams of molecules is what we're going to do first, right? And we'll do the old ones first from GCSE, like oxygen, nitrogen, carbon dioxide, methane, ammonia, hydrogen, hydrogen chloride. What else was there? Chlorine, I know I've missed one. Ammonia. Did I say ammonia? Okay, so we're going to cover those first and sort of draw them, just go over those. I know it's been a couple of years, so if you need help with that, I suggest you go to an old GCSE revision book. I actually have some in my room on the shelf if you want to lift them. They're the old, it doesn't matter. You can borrow those. Nobody's going to be touching them for a long time, and nobody has touched them for a long time. Okay, then we're going to look at some new molecules, right? So the idea would be that you could extend this to molecules that you haven't met before. Okay, and we'll also look at molecular ions, right? How to draw dot and cross or Lewis diagrams of molecular ions. So that is new, right? But the principles should apply to all of them. Okay, so after we've done that, right, once we've had plenty of practice in drawing diagrams, we're going to notice that the idea of atoms sharing electrons to get a full outer shell doesn't always apply. So no more to that, right? Really what you're going here for is atoms will have no unpaired electrons when they form covalent bonds. Right, what you'll find, you'll see it soon enough, you maybe seen it if you've seen the Seneca Learn, is that the sort of smaller non-metals, now beryllium's a bit of a weirdo because it does mostly form covalent bonds. You might, if you reflect back, you'll see that we never really talked about it in group 2. It was not mentioned. The reason is it does covalent bonding, even though it's a metal. We don't have to care why. Anyway, beryllium and boron, you'll find, will actually bond so that they have fewer than 8 electrons in their outer shell, but they will have an even number, right? Once they'll have all their electrons will be paired. You'll find that these guys here tend to just do expect pretty much. Yeah, oxygen, actually nitrogen as well. Okay, so no, they don't. Right, and then as they get bigger, as the atoms get bigger, you'll find that actually they can have more than 8 electrons in their outer shell. But as I say, they'll never have unpaired electrons. Never is a dangerous word in chemistry. You will not, hopefully not encounter them having unpaired electrons, right? And any particle with an unpaired electron, like atom or molecule, is very reactive. It doesn't hang around for long. Okay, so you've got this, no unpaired electrons. Now, when we've done that, so that really will extend on from the diagrams. Now, when we've done that, we're going to look at shapes of molecules. This is actually topic 1.6 on the specification. It's pretty difficult, but I think given that we'll be talking about pairs of electrons and the types of electron pairs, about lone pairs and bonding pairs, and that really relates to how the shape of molecules in 3 dimensions, I decided to put it here because I think it'll just follow on nicely from that. So what we look at really is how the number and type of of electron pairs dictates the shape, the 3D shape, and bond angle. Okay, so we're going to look at that. Basically, all electron pairs, the electrons stay together as a pair, but they try and push each other as far away as possible. So you end up with bonds adopting any shape that means the electron pairs are as far apart as possible. That's the theory of it. There's lots of shapes to learn. Okay, now once we've done shapes of molecules, right, we're going to move on to intermolecular forces. Okay, so we're sort of extending out from just the molecular. So we're really focused on the molecule, individual molecules, their bonding, the type of electron pairs, whether they have a full 8 electrons in their outer shell, and what shape they're going to adopt. And now we're going to extend it out, like zoom out and look at the connections between molecules. Now, there are 3, right? There's one that you've already heard of, which is van der Waals forces. Now, anybody who looked at the Seneca learning resources, they call them London forces in the English boards. In fairness to them, they are more correct. Van der Waals forces actually is not correct, but that's what we're going to use. Okay, so when they say London forces, you think Van der Waals forces. Okay, we have another type, which is called permanent dipole attractions. They do have to check that. They change it. Every time they change the spec, they change the name of these. Anyway, and the last type we have are called hand bonds. Okay, so these are the different types of connections you can have between molecules, and you need to be able to identify which ones are present and what effect that has on the physical properties. Okay, now physical properties really here is just melting point, boiling point, and solubility. So in the past we haven't really looked at the effect of bonding or connections between particles in terms of solubility. That is going to be a new thing at A level, which we already mentioned in passing with the ions. You should have seen that in your ionic bonding notes, the ion dipole interactions between ions and water, right? Anyway, the physical properties then are connected. So intermolecular forces dominate, or they determine the physical properties. Now, as part of that, we're going to look at the nature of the bonds within molecules, right? And we're going to come up with this idea of polar bonds. That's dominated by something called electronegativity, which is basically how much of a tug, right? If you have 2 different atoms, let's name them, say hydrogen and fluorine, right? Because fluorine has a much stronger pull on the electrons in the bonds, the electrons are going to lie much closer to fluorine. So we're going to discuss that, and that has an effect on what type of molecular forces there are, right? So that's properties. And then the very last thing, it's kind of jammed in, it's in 1.5. There's molecular covalent structures, which really, I have to say, when you see it, you'll see that actually all this is much more difficult than this. This is really just related to the structure, and it really is kind of based on the intermolecular forces and the overall structure and then the properties. Okay, so I mean, I have to say I put it after intermolecular forces because I think if it goes before it, I don't think it fits in, but we'll see. So that's the story of how we're going to develop covalent bonding. All right, so let's make a start. Now, you can read this yourselves. You need to know this definition. Slightly different to GCSE, where you had a covalent bond as a shared electron pair. It's still a shared electron pair, but now you're talking about electrostatic attraction between the shared pair of electrons and the nuclei of bonded atoms, right? So all that's saying is that you have right, supposing, let's draw the quickest, let's draw hydrogen, old GCSE version, okay? So if you have a hydrogen molecule, each hydrogen atom has got one electron, goes into the shared pair. Now I'm going to put in, so you've got a proton in the nucleus here, right? So each nucleus contains is positively charged. So the thing that's holding the electrons in between the atoms, the thing that stops them flying off somewhere else, is the attraction to the nucleus. We've met that concept before. Remember, in ionization energy, it's all about how tightly held the outermost electron is by the nucleus, or how far away. So it's the thing that you're fighting against, if you want to break this bond, is the nuclear charges. All right? Okay, so we've got definition, and then there's something here that should be very familiar, the idea of a single covalent bond, a double covalent bond, a triple covalent bond, and that's to do with the number of shared pairs of electrons. All right, so I'll let you read that yourselves. If you're not sure, please go onto Chem Guide or just on GCSE Bite Size, or just Google what is meant. But just be careful with your Google resources. If you put in single bond AS level or single covalent bond GCSE level, you'll get much better hits. If you might get university stuff otherwise, and you don't want to go there yet. Okay, so said here can be represented, right? So this is what we're going to work on now. You've got different types of representations now. Sorry, me has hopped over the page. Right, just be warned. Okay, so you should recognize these dot and cross diagrams and the line diagrams from GCSE. Now, just to note here that we didn't tend to do this, but we tend to, in the line diagrams, no, it's not consistent. If there are lone pairs, they are sometimes included on the line diagram. Now you can see here they haven't bothered, but you could put them in, right? So each oxygen atom in the molecule has got two lone pairs of electrons. In other words, electron pairs that are not part of the covalent bond. These are shared pairs. So there's two shared pairs. Right, and they're represented here. They're the in-between bits. And then you've got your lone pairs, which are represented here and here. Okay, and there you have. So this should be fairly straightforward. Okay, they're not very big. Okay, so you're going to have a go, right? So I've got a worked example here, right, from way back. So your chemical formula is that. Your dot and cross diagram is this. Now, I call it a dot and cross diagram, and I call these Lewis diagrams. Right? They're just a shortened version. Some people call that an energy level diagram, and some people call that a dot and cross diagram. Okay, but we'll try and make sure that either of those is acceptable, by the way, at A level. Okay, so let's have a look. So if you want, you can pause and just do these yourselves, or you can watch me do them until you're happy and then pause and do it yourself and then look at the final thing. But I'm going to work on with it anyway, all right? So you have got chlorine, right? Chemical formula, Cl2. Dot and cross diagram, right? Chlorine, each chlorine atom has 7 electrons in its outer shell. So 7 electrons means that it has 1 unpaired electron, so it'll form 1 covalent bond. And will I keep them the same? Okay. Now, I've just realized that I am leaping ahead here, assuming that you remember everything from 4th year. So I'm just going to actually take time to work through this. And so again, just fast forward through if this is easy for you. You just need to kind of work at your own pace, all right? But I know there's some of you who this is a long time ago since I actually done any of this. So just to remind you. Okay, so just to remind you with covalent bonding, right? Now we're going to kind of go with the whole, all of the ones at GCSE, we're assuming you end up with 8 electrons in the outer shell, right? So actually I'm going to represent our chlorine atoms first. Okay, so chlorine molecule, remember it's one of the diatomics, you need to know that. Okay, oh gosh, I'm being inconsistent. Okay, so the chlorine molecule is consists of 2 chlorine atoms. Now, I said there can be no unpaired electrons, so that's going to be true. So the unpaired electrons are going to be shared so that they become a pair. And then you end up, so the 2 of them will end up in a pair, and then you end up with this. I'm afraid I have been inconsistent, my dots and crosses, but remember, they all represent electrons. Okay, so number and type of electron pairs. Let's have a look at it. You've got, so you have 1 bonding pair. Okay, sorry, I've just realized I skipped on from the idea of lone pairs and bonding pairs. So can you just make sure that I call them shared pairs, I think, but actually I should just start calling them bonding pairs. So you've got 1 bonding pair and you've 1, 2, 3, 4, 5, 6 lone pairs in total in the molecule. All right. So methane, CH4. Actually, there's a very good video on YouTube. It's called Free Science Lessons. If you look up Free Science Lessons, covalent bonding, it's GCSE, but he talks very well through all of these molecules, right? And if you need some revision, I suggest, and they're very short videos, they're like 4 minutes long each. I suggest you work through those. Do not move on from this point without being comfortable with how you get to these molecules. Okay, so where are we at? I've missed something, haven't I? Number and type of electron pairs. So this time you've got 4 bonding pairs in the molecule, 4 shared pairs, and you've got no lone pairs. All right, nothing. Okay, ammonia, NH3. Nitrogen has 5 electrons in its outer shell. So let's give ammonia the X's and hydrogen's electrons are the dots. Okay, ammonia, this time you have 1 lone pair. I'm going to be very lazy and shorten it to that. And 3 bonding pairs. Water has got 6 electrons in its outer shell, but only 2 are unpaired. So it'll form 2 covalent bonds. And then it has 2 lone pairs and 2 bonding pairs. Now I'm writing it like that because actually the shape of the water molecule is going to be dominated by the fact that those boils exist, right? Carbon dioxide, CO2. So it's got carbon, each carbon needs 4 bonds, each oxygen needs 2, so they form and this time, now this is a bit confusing, right? Double bonds, we'll come back to this again, counts as 1 bonding pair. So it's actually got 2 bonding pairs. We will see this later, so don't worry too much about it for now. Okay, I suppose you could say that each connection between atoms counts as 1 bonding pair, and this is all to do with the shapes of molecules, so don't worry too much. It is a double bond, but for the sake of shapes of molecules, it actually counts as a bond pair. Oxygen, O2, so there's a double bond between them, and lone pairs. In this instance, you've got 4 lone pairs and you've got 1 bonding pair because just 1 connection. And lastly, nitrogen is N2. It's a triple covalent bond. And each nitrogen, then the other 2 electrons are in lone pairs. So it has 2 lone pairs and 1 bonding pair by the fact 1 connection. All right. Okay, now I'm going to stop at that point and this video out, and then I will do the next one.